Okay, I just want to acknowledge input from Dima Domajay, Sugata, and Joe Brown. Just, I suppose, talking through a few of these issues. I suppose I've been talking with Dima, who's got the office opposite the hall, and we talk about this kind of stuff quite regularly. So I suppose I'm going to kind of break this into kind of two parts and try to answer the question, why do we care about the tropics, like modelling the tropics? And the first slide is the first section is just on seasonal or interannual timescales, and it's going to be very brief. I mainly want to focus on, I suppose, projected changes for the future, and particularly that spatial pattern of climate change. So I think just if you think about, well, why do the tropics matter? I think you can pick up the newspaper. It almost feels like in any week from the last 3 years, and there would be a study about the El Nino Southern Oscillation, or the Indian Ocean dipole, and talking about the climatic impacts of that. And I think it's kind of really clear that it plays a role in kind of modulating our extreme events. So if you think about the distribution of rainfall, for instance, the extreme ends of that distribution are at least partly shaped by kind of these events. Maybe not whole, and maybe there's a debate about how much you're kind of talking about, but it's playing at least some role in that. So if we want to get the distributions of our rainfall right, wherever it is you're of interest in Australia, you really need to kind of get this kind of variability correct. So I think it's really important for understanding now. We can think about, maybe what's happened in the last 3 years or the last 5 years or whatever, but we also want to get that right for the future. When we're starting to think about, well, what's the climate actually going to look like in the year 2050 or the year 2070? If we don't have kind of the right background variability, how can we really get a sense of what things are going to look like? All right, but the main kind of focus I want to talk about is this kind of projected pattern of climate change. So this is the pattern here. The color is not kind of really working out. What you should be able to see is kind of this kind of clear enhanced warming in the eastern and central equatorial Pacific. So the region we typically refer to as the cold tongue. Here it's just coming up as a uniform kind of dark red. And I think, what a lot of the papers, I suppose, have referred to kind of the warming pattern as having like an El Nino-like kind of warming. So it kind of looks like an El Nino event. There's kind of this concentrated warming in that eastern central Pacific. So kind of giving some context about why we would even care about the warming in that region relative to everywhere else. So there was a study by Kostiker and Shi, I think it was 2013, and they basically just used a model, and they kind of, it was a partially coupled model, meaning that it was not a partially coupled, it was a pacemaker model. And then, so in this kind of purple boxed region, they had the observations were prescribed in that region, and then the model was kind of left to freely evolve outside of that region. The time series on the left-hand side show the orange, so the red line is the global mean temperatures from that ensemble simulations that are nudged towards the observations just in that small purple box. The black line is the observations, and then the purple line there for reference is the unnudged kind of model. Okay, so you can see that the one that's nudged in that kind of small purple box does a really good job at representing what has occurred in the observations. So if you focus on just the two, I suppose, kind of box plots and the end. So this is, model trends or model temperatures for the year 2012, and you can kind of see that the observed kind of observed black line is basically falling outside of the 95% confidence interval of the model that's not nudged, whereas it's kind of well within the model when it is nudged back to that historic. So highlighting, how important that kind of small region is. We can then look at studies that talk about, I suppose, how the relative warming, so the warming in the Western tropical Pacific, where we got a lot of convection, is basically directly related to the climate sensitivity. So they can show plots like this for CMIP7, where you've got an R squared of 0.6, larger than 0.6, kind of saying that relative warming in that Western equatorial Pacific is really important for the climate sensitivity. That relationship kind of changed a little bit moving forward to CMIP7, and I think some of that was due to the kind of cloud aerosol impacts that were in the model, but it still existed. And I think they kind of said that there was more of a role for the Southern Ocean in CMIP6, but still the tropical Pacific is kind of an incredibly important location. We can also think about, maybe projected changes in the mean state. So we're, here in Australia, we really kind of want to know, what will the rainfall be, say, over Northern Australia? And if you have a look through the models, I think it was, I can't remember who presented it yesterday, that was kind of looking at the monsoon region, and it basically had this spread of models. Basically, half the models are very dry or dry, half the models are wet, and there's kind of no real consensus as to which way you're kind of thinking this region is going to go. So again, thinking about, so we don't really know what the rainfall is going to do, but what we do know is if, there was this study by Joe Brown with the figure here, looked in CMIP7 models, and basically when they separated the models into those that were dry compared to those that were wet, so the difference in the dry and the wet is on the left-hand side, and what they got when they looked at the sea surface temperatures, what they got is this plot on the right-hand side saying those that kind of basically warmed in that Western Equatorial Pacific more than the others, they were the ones that turned out to be dry. Okay, so the warming in this kind of, Western Equatorial Pacific region, again, being kind of very important for the, I suppose, the projected rainfall changes for the Australian region. If we, I suppose, want to move forward and forget about just think, oh, well, maybe the mean state's important, but we also want to care about variability. Again, we kind of come back to this region and that kind of El Nino-like warming pattern. And model simulations suggest that there's an amplification of the atmospheric response to El Nino events. And what does this really mean? It means that even if we don't have a change in the amplitude of the El Nino event themselves, we're expecting to have more tropical precipitation. So the precipitation response is going to be larger in that region. The knock-on effects of that are, we would expect that the teleconnections of the El Nino events will be larger. So for a given, say, 1 degree Celsius El Nino event, the tropical precipitation response is going to be larger, and the teleconnections will be larger. So this is depicted in this 2 panels here in the bottom. So the left-hand side is just what happens when you regress NINO 3-4 sea surface temperatures onto precipitation. And this is, CMIP6 ensemble mean kind of regression map. And the plot on the right is showing that kind of precipitation map differences when you're looking at the SP585 kind of scenario minus the historical scenario. And you can kind of see there's an intensification of the precipitation along the equatorial region. And you can also see some changes globally. The one thing I want you to know is anywhere you see an asterisk, which is kind of black, that's indicating there's an amplification that's significant above the 95% confidence level of the historical teleconnection. So you can kind of see there's very few regions that are hatched in that kind of the magenta color. The magenta color is saying there's an enhanced dampening of that teleconnection. So you can see lots of, approximately 39% of the globe is showing a change in the teleconnection, and I think the large majority of that is an enhancement. The reason I bring that up is because that entire kind of response of the tropical system is at least, I think, largely brought about due to that background warming pattern, the fact that it's El Nino-like compared, there's that El Nino-like kind of warming. It changes the zonal gradient of sea surface temperatures on the equator. It changes the meridional gradients of sea surface temperature on the equator and makes that precipitation response easier to come about. So the precipitation response for the large events comes about easier at lower thresholds. All right, so we kind of got to this point. The region matters, right? So maybe I took too many slides and too many minutes to tell you the region matters. And then we can kind of say, well, how do the models actually go about representing kind of the trends in this region? And there are a lot of studies that looked at this. This is just one by Coates and Karnauskas in 2017. We have kind of 5 different observational products depicted here. This is the observed trend between the period 1900 to 2013. So you can see 2 of the products have kind of a little bit of a cooling in the Eastern Equatorial Pacific. One of them is kind of pretty neutral. So that bottom left one is kind of pretty neutral in the Equatorial Pacific. I'm way too long. Sorry. So I'll get to the point. So the bottom panel is what you're getting from the model trends. And I suppose the point here is if you have a look at the gradient between this box along the equator, so this left box and the right box here, the model range is depicted here by the gray shading. The dark gray shading is the 25th and 75% confidence level. The light shading is the 5th and the 95% confidence level. The 5 different observational products are here in the pink range. You can see there is no overlap between those 2 at all. It turns out there's 83 simulations from 41 models, and I think only 4 of them kind of overlap in that kind of range where they might be kind of, consistent with one of them, one of those kind of observational products. So there's kind of a large discrepancy here. You can say, well, actually, observations from 1900 are pretty poor. Okay, so I don't really agree with this. You can kind of look at different studies. So there's one that's from, I think Richard Seeger, starts from 1950, does something similar. They get the same result. There's this one here by Jingjiao Lao, starts in 1980, they get the same result. So it's kind of this, there's a real consistency of message that kind of says it doesn't look like it's going to be an observational problem. It looks like, there's kind of something happening in there that maybe more points towards the models. So that's the main point. And then you kind of go, well, what could the potential causes for this model discrepancy be? And we can say model underrepresentation of internal variability. So the models just don't have enough variability on these kind of long timescales. That could be the cause. Obviously, that's going to be, yes, we know that exists. We know that happens. Everybody, I think there's lots of studies. So these 3 or 2 studies here, so one by Greg Kochoba and Scott Power, and one by Ben Henley, show that models underestimate decadal variability. From my perspective, this is more likely going to be of impact when you're looking at these shorter term trends, so the 1980 to present or 1990 to present, less likely when you're going from 1900 to present. So maybe that definitely plays a role. Maybe definitely, I just said. The other one is the observations are in error, okay? If we're focusing on the 1900 to now, yeah, that could definitely play a role. Okay, there's definitely discrepancies between these observational products. So it could be it, but as we focus on this kind of shorter term record, we've got, more confidence in our observational products. So here we are. And then the final one is the model response to anthropogenic forcing could be wrong, could be incorrect. Maybe we've got the correct response for anthropogenic greenhouse gas response, we've got the correct aerosol response, but the balance between them is a little bit off. So we might be getting the right patterns, but we kind of get this incorrect weighting of both of those forcings. And there's lots of kind of studies out there that suggest this is at least possible. So there are studies by Richard Seeger in 2019, kind of with a simple model, showed when they nudged the background state of the model, they got a very different pattern projected moving forward, suggesting background state biases could play a role in kind of this pattern. So the fact we're getting a consistent pattern from the models might be because the models have consistent background state biases, rather than they're actually representing the processes required. And then there's also the possibility that the forcing applied to the models may be deficient in some way. When you think about this, I haven't really explored it here, and I haven't really thought about it. And this is something that's going to be more likely, at least in my mind, from the aerosol contribution, because it's so spatially variable. I think greenhouse gases are kind of quite well mixed. So it's something that, is probably less likely to impact a spatial pattern, but I think aerosol forcing is kind of, I'm not going to say poorly constrained, but not as well constrained, I think would be the words. So that's it for me. I'm way too long, sorry.
Great.